Hello, I'm Razvan Marinescu, and I'll present my PhD work, which was titled Disease Progression Modeling of Alzheimer's Disease Subtypes. Before I start, let me tell you a few words about myself. So I was born and raised in a small town in southern Romania called Pitești, and I went to study in the Brătianu High School, and after graduating from the high school, I went to London to study for a 4-year MNG degree in computer science at Imperial College. Afterwards, I went to study a master and a PhD in medical imaging at UCL, and I've been working with Professor Daniel Alexander on disease progression modeling. And this is the building where I currently work. It's a very nice picture with a lot of, on a very sunny day in London, and it might seem unbelievable, but we do have a lot of sunny days in London, and it's contrary to what some people might think. So before I start, let me try to break down the title of my presentation. And in order to explain what it actually means. So first of all, let's talk about Alzheimer's disease. So Alzheimer's disease, or AD, is the usual cause of dementia in most of the cases. And the symptoms are usually memory loss or any kind of memory problems, but the patients also have other problems such as language and so on. And we know there's many causes of Alzheimer's disease. First of all, genetics. We know that many genes such as APOE are involved, which can increase the risk of developing AD. Another cause are neurofibrillary tangles, which are caused by tau aggregation in the brain. Amyloid beta misfolding is also known to cause AD, and there's many other risk factors like vascular disease and Lewy bodies, which can eventually lead to Alzheimer's disease. Now let's talk a bit about Alzheimer's subtypes. What do we mean by subtypes? As you may know, there are many known subtypes or variants or any related diseases to AD, such as posterior cortical atrophy, frontotemporal dementia, and many others. Let me talk a bit more about posterior cortical atrophy, because this is going to be a focus for my presentation. So posterior cortical atrophy, or PCA, is considered an atypical visual variant of Alzheimer's disease, where subjects usually have visual deficits. They can't read, they have blurred vision, or they can't navigate around space. And in terms of atrophy patterns, these are mostly focused on the posterior part of the brain. So you can see in this picture, this is where in the posterior part of the brain where most of the atrophy lies. And this is in contrary to typical AD, which also shows a lot of temporal involvement. And finally, I wanted to say that a PCA is very rare, since only around 5% of all AD cases have PCA. Now, what do we mean by disease progression? By disease progression, we mean being able to estimate the biomarker evolution across the disease time course. So this is a famous picture from the ADNI website, which shows the progression of several biomarkers across a clinical disease timeline. And it shows how many biomarkers go from a normal state to an abnormal state. And this is very important because some biomarkers, such as amyloid beta or tau, become abnormal much earlier, very early in the disease process, in the preclinical stages, so before any symptoms become evident. And this is really important because we currently believe that in order to develop efficient drugs, which will show any benefit, these would have to be administered as early as possible. Now, what do we mean by modeling of disease progression? By this, we mean using a mathematical model to quantitatively estimate disease progression. And here's a cartoon of several measurements taken for 3 subjects, and these are longitudinal measurements across several visits. And what such a model would do is just to fit a line, the black line, between these measurements. Now, this is very nice. It doesn't seem too hard to do this, but in practice, it's a bit more complicated because we don't really know the stages that the patients are at when they come to the clinic. What we have instead is the picture on the left, where we just have the measurements that are, we don't know the disease stage, we just know the time since baseline visit. So it means they're not aligned on this temporal axis anymore. And it's much harder to actually see any trend here. And it's even harder with real data, where you have many measurements, and and we call this plot on the left a spaghetti plot, because it looks like spaghetti. So we need some kind of model to be able to go from this picture on the left to the one on the right. And this is what a disease progression model would do. And it will also account for many other challenges, such as the fact that biomarkers have different trajectories, or that the cohort is heterogeneous, because, for example, patients could have different underlying pathologies, such as Lewy bodies and so on, that could cause Alzheimer's disease. And also the control population is not well defined in some cases, because we could include amyloid positive subjects. So the model will have to take that into account as well. So the aim of my PhD was to study the progression of atrophy in two diseases. One of them was Alzheimer's disease, and another one was posterior cortical atrophy. And what we wanted to do was to get a picture of like this, where we can find the order, we can see the order in which regions become affected by the disease, and how affected they become at different stages, where white represents regions which are normal, and the blue represents regions which are abnormal. And another aim of my PhD project was to develop and improve novel disease progression models, which usually involve some mathematics, as you can see in this equation. The reason why we were doing all of this was because we believe this will enable more accurate patient staging and prognosis, and this would also help the development of potential drugs. So these are my contributions throughout my PhD. First of all, I studied the progression of posterior cortical atrophy and typical AD using two models. One of them was an event-based model, or the EBM, and another one was a differential equation model, or the DEM. And afterwards, I've also looked at evaluating the performance of several of these disease progression models in order to be able to say which one is better at particular tasks or according to different criteria. I've also looked at developing a vertex-wise progression model, which can estimate very fine-grained spatial patterns of atrophy. And finally, I also looked into I've also organized a tadpole competition, which is a challenge that is aiming to predict the evolution of patients at risk of AD. So now let's talk a bit about the event-based model, the EBM. So here we were interested to find out the order in which gray matter regions become atrophied in PCA and typical AD. That was our clinical question, where we started from. And for this we used a very unique cohort from the Dementia Research Center, which had a really large number of PCA subjects, around 70 subjects. And this is a really large number given the fact that PCA is rare. And I was very excited to actually work with this data set. And this work has a really huge potential impact, because it will be the first major investigation of PCA disease progression, and the findings could potentially inform the selection of measures in clinical trials in PCA. So in order to look at the progression of PCA and typical AD, I used the event-based model, as I said. So the event-based model, or the EBM, models the progression of atrophy as a sequence of abnormality events, which are informed by underlying biomarkers becoming abnormal. So what we do is that for each biomarker, we fit a mixture model of two Gaussian distributions, one for normal values in green and one for abnormal values in red. And we repeat this for every single biomarker, and then we find a sequence in which all these events become abnormal, using by estimating the likelihood of each sequence and selecting the sequence with the highest likelihood. So the likelihood of the sequence is given by this model. You can ask me more on this. I'm not going to explain it, but you can ask me if you're interested. And we just select the sequence, find a sequence with the highest likelihood using a greedy ascent method. And we also apply Markov chain Monte Carlo methods to estimate the uncertainty in this sequence. And here are the results on PCA and typical AD. And what we find is that the occipital and superior parietal regions become abnormal first in the PCA subject, whereas in typical AD we find that the parahippocampal gyrus and the inferior and middle temporal lobes become affected early in the disease. And next we wanted to do a bit more. We wanted to look at PCA subtypes. We wanted to see how various patients within the PCA cohort progress over time. And for this, we actually split the PCA cohort into 3 subgroups, based on cognitive tests. So the first subgroup had the basic visual impairment based on cognitive tests. The second subgroup had spatial perception impairment, and the third subgroup had the visual perceptual impairment. And we also had some initial hypotheses on regarding which regions would be affected early in each of these subgroups. And we ran the event-based model on each of them, and what we found is that the regions that appeared early in the progression of each subgroup actually matched with our initial hypotheses. And this was really great because it was showing that actually PCA is it's not actually a homogeneous group but a more heterogeneous group. It doesn't actually mean that these should be taken as completely distinct subgroups, but they could actually be more like points on a phenotypical continuum of variation. Alright, so one problem with the event-based model is that it doesn't tell us anything about the rate of atrophy, how fast the atrophy goes in the brain. So in order to actually look into this, we use another model called the differential equation model. And this model works as follows. So we fit a linear trajectory to every subject from longitudinal measurements of every subject. We extract the slopes, which we plot against the average biomarker value. And then we fit a non-parametric curve to these measurements, such as the Gaussian process. Afterwards, we integrate this non-parametric curve to get the full biomarker trajectory, which is then aligned on the temporal axis aligned with the other trajectories on the temporal axis. And here are the results of the differential equation model on the PCA and typical AD. What we observe in the PCA again is that, as we saw earlier with the EBM results, we see that the occipital and the parietal regions become abnormal early in the disease process, and they show extensive atrophy. Whereas in AD we have a much more global pattern of atrophy where many regions become abnormal at the same time. And we see in particular that the hippocampus has a very early involvement, which is very noticeable. This is and we also showing similar results, but just compared side by side for each region for PCA and typical AD. And for example, we found that the occipital lobe, as expected, becomes abnormal much earlier in PCA, which is the blue curve, compared to typical AD, which is the red curve. And the opposite is the case for the hippocampus, where it becomes affected much earlier in typical AD compared to PCA. Alright, so this is great. So now we looked at the progression of these diseases and with 2 models already. But we can't really tell which model actually performs better at various tasks like staging subjects or at predicting future biomarkers. So what I looked into next was to actually evaluate their performance at various tasks. So as I mentioned previously, actually, many other disease progression models have been proposed in the literature. These are some of them. You don't have to read them through it in the table. But what I want to mention is that each one of them have several advantages and limitations. And what I wanted to do was to just to assess, implement some of them and try to see how well they perform with respect to various criteria. So I implemented improved fitting procedures for two methods, for the event-based model and for the differential equation model, and I tested to see if these improved procedures perform better than the original versions. And furthermore, I also defined some performance metrics. So I defined the staging consistency metrics, which actually measure how, they actually measure whether stages of a subject at follow-up are greater than the stages at baseline for patients. And this is in line with our understanding of Alzheimer's disease as a progressive disease. And I also defined another class of performance metrics that I defined was the time-lapse stage performance metric. And this is testing the models on how well they estimate the time that elapsed between two visits. And here are the results on our implemented methods. And what we found was that the event-based model novel methods perform better than the standard methods, and this is significantly better. Whereas the differential equation model optimized version does not perform significantly better than the standard model. And these the same results are we've had similar findings for both the PCA and typical AD patients in the DRC cohort. And now I'm going to skip the fourth part, which is developing, which is on the vertex progression model, because I've already rehearsed this for IPME. I'll just move straight to number 5, which is the tadpole competition. So the tadpole challenge is a challenge which is aiming to predict the progression of individuals at risk of AD. And participants can use data from ADNI of various sorts, and they have to implement some models that can take this data, learn from it, and then predict future diagnosis and other types of measurements that we require. And they can train the models again on existing data from ADNI, and then of course they will predict future values for the next 5 years. And my work on the challenge was to first of all assemble the training data sets from several ADNI spreadsheets, and actually ended up with a spreadsheet which had almost 2,000 features. It was really, really big, and it wasn't actually easy to do the merging and make sure everything was correct. I've also helped create a website which provides a lot of useful information on the challenge, and I also finally built an automated evaluation system and the leaderboard like in a kind of competition, where our participants can make a submission using existing data, and this automated system will evaluate their submission, compute the results for every single criteria, and publish it back on the website in the leaderboard. Alright, and I'll finish by saying that you're welcome to join the challenge and tadpole challenge and find more information on our website. And finally, I'd like to acknowledge my supervisors for helping me throughout my PhD, my collaborators in my research group, and finally my funders for making this work possible. Thank you.